All right, good morning, good afternoon, good evening. This is Dr. Kaz from an undisclosed secret location down here in Florida. And I'm going to pick up from the last class. This is the day 2. We're going to be continuing with chapter 2 on ions, molecules, macromolecules today. And I kind of want to just go back a little bit and finish up the concept of electronegativity when we're talking about covalent bonds. So jumping back to this slide here, when we talk about electronegativity, I want you to think of an element's trait of being selfish. And it's selfish because it wants to hog or pretty much hoard the electrons in a covalent bond. And as you remember, a covalent bond is a sharing of 2 electrons or a pair of electrons. So a molecule that essentially is going to be more electronegative is going to actually pull the pair of electrons closer to its nucleus and further away from whatever the other element or atom's nucleus would be. Okay, so you'll see that there will be, in some cases, an unequal sharing of electrons, and in some cases there'll be an equal sharing of electrons. That equal sharing of electrons, or that equal attraction there, we refer to that as a nonpolar covalent bond. Okay, so when those paired electrons are kind of in between or equidistant from each element or each atom, then we have a nonpolar covalent bond. Now, when we have the electrons that are shared unequally, meaning that those paired electrons will be closer to one element or atom more than the other, we refer to that as a polar covalent bond. Kind of felt that I didn't make myself clear enough on that last class, so just kind of wanted to clear that up. So when we're looking at the periodic table and we want to notice the trait or the pattern of increasing electronegativity, it's like reading a book, all right? So as we move from left to right, all right, across the rows, remember the rows go from side to side, okay, on our periodic table, okay? As we move from left to right, we will notice an increase in electronegativity. And as we go from bottom towards the top, we will also notice a trend of increasing electronegativity. Okay, so in our body, all right, when we're talking about the 4 common elements, all right, hydrogen, carbon, oxygen, nitrogen, all right, all of those common elements, we've arranged them here at the bottom of our page in order of least to greatest electronegativity. So you can see that hydrogen is the least electronegative and oxygen is the greatest. So oxygen is the more selfish of the elements, and it's going to want to pull all of its shared covalent bond electrons closer to itself with whatever it's sharing. So when we were looking at the water, for example, H2O, our molecular formula for water is H, okay, 2O, so obviously hydrogen, all right, the 2 representing that there's 2 molecules, and then oxygen is going to be 1 single molecule. So when we actually draw that out, all right, those shared electrons are going to be pulled closer towards the oxygen than it would be closer to the hydrogens. So the molecule kind of looks like this, all right? So this end of the molecule, because it's going to be pulling more of the electrons closer to it, is going to have a negative charge, and this part of the molecule between the hydrogens or near the hydrogen ends, that's going to be positive. So it's actually going to be considered a polar molecule. You can see, right, closer to the oxygen, more electronegative, and then further away towards the hydrogens will be less electronegative, and therefore it's going to be more of a positive charge here. So that brings me to this slide here. Electrons, as we all know, have a negative charge. So the more electronegative atom is going to develop what we call a partial negative charge, and that's what we saw with our oxygen, with our water molecule on the previous slide that I drew out. And I'll try to represent it again here, but it won't be as good. All right, and then the less electronegative atom or atoms will have a partial positive. So you can see the symbol that we use, all right, is the Greek delta, and I'm not even going to try to draw that. It's already listed here, all right. That's going to kind of show you, defer that electronegativity, okay. So just kind of, if you're still not sure, just kind of rewind the video and check out some of that information there in regards to electronegativity. It is kind of important to understand that, because we're going to talk about polar versus nonpolar molecules trying to cross over the plasma membrane. That will be more in chapter 4. But I want to move on to the next subject here, and talking about water. First of all, water is considered to be the universal solvent, and a solvent is going to be the actual solution in which substances will dissolve into, if they can. All right. So I liken it to, at my house, I'm the person that would wash dishes from time to time, and I have been known to soak pots and pans. And the reason why is water will actually work on those bonds between the food and whatever is in the pot or the pan, and over time it'll break those bonds down, and so it kind of dissolves whatever what it is that was cooked in, and so it makes it a little bit easier to clean. So we're going to find out as we move on in later on in this course, that there are going to be substances that do not dissolve in water. Okay, and those substances that do not dissolve in water are going to be non-polar molecules. Right? We refer to those as hydrophobic. If you have a phobia, you have a fear of something, hydro being water. So we refer to those as water-fearing, hydrophobic. And those nonpolar molecules fall into that category. Okay? Now, substances that do dissolve in water, this is important, are going to be polar molecules. All right? So we refer to those as water-loving or hydrophilic. Hydro, again, being water, philic being loving. So those are hydrophilic, and they will dissolve into water or disperse in water. All right, so polar molecules fall into that. Ions fall into that too. All right, you know an ion is a charged element, all right, because it's lost or gained electrons, okay? So just kind of refresh that. So we're going to talk about water being a neutral solvent, and this is going to lead us into acids and bases in the pH scale here. So it's kind of important that we kind of know some of the basics here when we're moving into this information. So one of the interesting facts about water is that just randomly, it will spontaneously dissociate. And what that means is if you go all the way down to the bottom of the page here, as I'm circling this formula here, you can see there's your water molecule. And what will happen is that water molecule will kind of just break apart on its own. And it's going to form, all right, a hydrogen ion, all right, the H plus there, and the OH negative, that's called a hydroxide ion. All right, so it's important that you understand those terms, okay? Hydroxide ion is going to be OH negative, right? And then our hydrogen ion, all right, that's going to be the H positive that we see there, okay? So that's what we're talking about when water spontaneously dissociates. The bond between the oxygen and the hydrogen, it's just going to break apart on its own, randomly. You can see the statistic there, 1 out of 10 million, all right, ions per liter of water, okay? So this other formula here is just showing you two water molecules and what happens. Because from time to time when one water molecule dissociates, that hydrogen ion that's listed here, well, hold on. That hydrogen ion here is going to find another water molecule and just kind of glom onto it and form what we call hydronium. Okay, hydronium is H3O. Okay, but the real important concept that I want you to pay really close attention is this guy down here. Okay, that one water molecule will spontaneously dissociate, just break apart, and you'll have equal parts hydrogen ion and then equal parts negative hydroxide ion. Okay. All right, so that leads me into this concept here of acids and bases. And this is important that you understand the definition of acids and bases. So an acid, again, using that term dissociate, all right, in which the molecule will just spontaneously just break apart, all right? With an acid, it's going to produce a hydrogen ion, an H+, and an anion. And remember, an anion is a negatively charged ion. Okay, so molecule X or whatever. So going back to here, that's what we're seeing in this previous, all right, equation here. Here's our water molecule. So when it spontaneously dissociates, we have our hydrogen ion, our H+, and then we have our negatively charged molecule here, all right, our anion, the hydroxide ion. Okay, so that's basically what we're talking about here, all right, when acid dissociates in water. Okay, so I'm not saying that water is an acid. It is not. It is not. Okay, that's probably a bad example I should have got. Well, the better example down here is hydrochloric acid. All right, and I'll go over that. Okay, so when we're talking about acids, first of all, you want to know this term here, proton donor, because another name for that positively charged, all right, hydrogen ion is a proton. I know this can be confusing because we just learned that protons are subatomic particles. Yes, they are. The protons live in the nucleus of an element or an atom. Okay, but also scientists love to be confusing. Okay, and so they also decided to name the hydrogen ion, the H+, a proton. Okay, so acids are proton donors, which means that they'll donate or give up their H+ ions there. Okay, so if we dump a bunch of acid into a solution, all right, when it goes into that solution, it'll spontaneously break apart, and what will happen is it'll increase the concentration of all these free hydrogen ions just floating around. So when we look at the chemical equation here, all right, for hydrochloric acid, HCl, what will happen is HCl, right, when we add it to a solution, it'll break down into hydrogen, or hydrogen ion, H+, and then our anion, which would be chlorine, excuse me, and that'll be our Cl negative. Okay? So keep that in mind. So the easier it is, or the more dissociation, okay, that's the popping off of that hydrogen ion, we'll see that with stronger acids. Okay? The weaker acids will show less dissociation. So hydrochloric acid is a relatively strong acid. Right, our stomach actually produces that. Okay, and we'll see that it has a very low pH. We'll talk about pH here in a moment. Now, carbonic acid is an acid that we see in our blood. Okay, and you'll talk more about that in Bio 211. All right, that carbonic acid, all right, is a weaker acid. And there's certain situations in which we want to have strong acids, and there's certain situations in which it's more beneficial to have a weak acid. Okay, so this equation here at the bottom is great to show you here. All right, when we take substance A, that'll be our acid, and we dump it into water, it's going to dissociate into that hydrogen ion, all right, and then that anion, that negatively charged ion. Okay, so a base, all right, is going to be something that doesn't donate, but it accepts those hydrogen ions. So I tell folks, think of a base as like a sponge for hydrogen ions. It likes to suck them up like a vacuum cleaner. Okay, so we refer to bases as proton acceptors. And so when you add a base to a solution, it's going to decrease the concentration of all that free-floating hydrogen ions because it's going to want to suck it up like a sponge. Okay? So the more powerful or the more absorption of hydrogen ions we'll see that with stronger bases. Weaker bases will see less absorption. Okay, so ammonia and bleach, that's why they're very potent and great cleaners, okay, because of that property. They're a strong base, all right? And then our weaker bases, and again, we'll see these in our blood because it's really important that our blood maintains a certain pH, and that's the scale that we use to measure how acidic something is or how basic something is, all right? It's really important that we have, all right, these weaker bases to help maintain a certain level of pH in our blood, but also we'll see, all right, these weaker bases present in some of the secretions of our small intestine, because as food exits the stomach, there's a lot of there's acid in the stomach secretions, hydrochloric acid, all right, amongst other things. And so we need to start to make it less acidic. Okay, we want to get to what we call the neutral range because we do not want to cause damage to the tissue. So we have these weak bases there that help with kind of what we call neutralization. Okay, and it's helpful in trying to decrease the acidity. So here's when we add substance B, a base, all right, to water, this equation kind of shows us here's the free-floating hydrogen ions, and that base is going to attach itself or absorb that hydrogen ion there. Okay? All right, so the question here is what type of substance releases hydrogen ions when added to water? All right, that's going to be an acid. An acid is a proton donor. It's going to provide hydrogen ions to a solution, whereas a base is going to kind of suck it up. Okay? All right, so we're looking here at pH and neutralization, the action of buffers. It's an important concept to understand. So this is where we're going to move into what pH is. And it's a scale that we use to measure, all right, hydrogen ion concentration of something. Okay? So the pH scale is going to tell us pretty much how much hydrogen ion, all right, is present in any given solution. Okay, so the range that we have is 0 to 14. So directly at the center of our scale, all right, is going to be 7. So 7 is the value that we use to describe something that is neutral, okay, which means it's not acidic and it's not basic. It's right in the middle, okay? And so plain water is actually going to be neutral. Because remember, going back to the earlier slide here, the first slide that I started talking about, here, all right, water, right, when it dissociates, all right, is going to dissociate into equal parts of hydrogen ions, and it's going to dissociate into equal parts of hydroxide ions. So one molecule of water will give us one positive hydrogen ion and one negative hydroxide ion. So both of those will cancel each other out in relation to their charges, and we'll have a neutral solution there, okay? Equal parts. All right, so this is a very important concept here at the bottom. pH and hydrogen ion concentration are inversely related. And what does that mean? It means when one value goes up, the other one goes down, okay? And that's due to what we call the inverse of the log. All right, the really important part of these last two bullet points at the bottom of the slide here. So as the hydrogen ion concentration increases, the pH value decreases. So acids, when we add them to a solution, they're going to increase the hydrogen ion concentration. So therefore, all right, acids have a low pH value, okay? And then as the hydrogen ion concentration decreases, all right, the pH value is going to increase. So bases, when we add them to a solution, they go around, they're like Pac-Man, and they're going to gobble up or absorb all the free-floating hydrogen ions. And when they do that, all right, they're going to increase the pH value. So bases have a high pH value, okay? So looking at this next scale here, that kind of explains it to us. All right. So solutions in which we have equal concentrations of H plus and OH negative, okay, like water, for example, like I showed you, are going to be considered to be neutral. So they'll have a value of 7, because remember, 7 is right in the middle. 7 is the neutral value, okay? So in solutions where we have a lot of our hydrogen ions, all right, and a little hydroxide ions, they're going to be acidic. So they're going to have a low pH value. And then conversely, solutions that have more hydroxide ions or low concentrations of hydrogen ions, those will be basic, and they're going to have a high pH value. Okay. So just a common fact here, all right, when we move from one value on the pH scale, so when we go from 7 to 6, that's a 10-fold change, okay? If we go from 5 to 4, that's, just keep in mind, a 10-fold change. So when you go from one number to another number, it's a 10-fold change, okay? So looking here, I love this picture here, because this picture here kind of shows us a couple things. It shows us the hydrogen ion concentration, and it also shows the pH value scale here, okay? So as you notice, this hydrogen ion concentration in this beaker, we see a lot of hydrogen ions floating around. So it has a high, all right, hydrogen ion concentration value there, okay? So therefore, it's going to have a low pH value. You can see some of the examples here. Hydrochloric acid, pH value of 1. Well, guess what? That's in your stomach. All right, that's enough to burn through the table that you're sitting in class. Okay, all right. So stomach acid, 2 to 3, wine, grapefruit juice, I'll let you read those. Okay, but you can see that those have low pH values, so those are relatively acidic. If we go over here to our picture, they have a high hydrogen ion concentration floating around in that solution. Now we go down here to this beaker, it shows just a few hydrogen ions. So we can say that solutions that have a low hydrogen ion concentration, right, you'll have more hydroxide ions, okay? They'll have a high pH value, okay? So they'll be basic. And you can see sodium hydroxide, for example, bleach, ammonia, all right, antacids when you have an upset stomach, or what we call acid reflux. People will take antacids, which are just bases, and they go in there and they neutralize, all right, that acid. And then don't forget your neutral value, all right, of 7, that's pure water. Okay. So again, just kind of look that over. This picture here can be very helpful in that regard. Okay. So let's move into this next concept, a very important concept. All right. There's actually 2 concepts I want to talk about. Okay. You got neutralization and buffering. Okay. So neutralization, basically, what we want to do is we're in a situation in which a solution becomes either too basic or too acidic. And what we need to do is get that solution, all right, back to the neutral value of 7. Okay? So if a solution becomes, all right, too acidic, all we have to do is add a base to it. Okay? And vice versa. If a solution becomes too basic, then we need to add an acid to it. So like I was mentioning before, all right, when you get that acid reflux, all right, when you're producing too much stomach acid, all right, you can take an antacid. Tums, for example, is great. All right, specific medications that are going to contain a base, and that base will then help to neutralize that acid by, we call it neutralizing, because we're moving our pH value towards the neutral value of 7. Okay? So keep that in mind. If something needs to be neutralized, if it's too acidic, add base. If it's too basic, add an acid. Okay? Now we have lots of systems in our body all right, that are dependent on a specific pH. It's very important. So one of the solutions to a problem is to never have a problem in the first place. So what I mean by that is, all right, the concept of buffering, all right, helps to prevent the pH from changing to begin with. So if the pH and the normal pH value in our body is in this range, 7.35 to 7.45. So basically 7.5 on average. The pH of your blood wants to stay within 7.5, all right, that value. So if it starts to shift in any one direction, right, your body, all right, has what they call buffers, all right, to prevent that pH from shifting too much. Okay, so it's similar to neutralization, all right. But see, with neutralization, you already have an acidic solution or a basic solution, all right, to start off with. Well, in this situation, what we're doing is we're starting off relatively neutral or staying within that neutral range, all right? And what happens is something happens and you start to shift into an acidic pH or a basic pH. And so your body has, all right, these buffer systems that help to prevent it from getting outside of that normal range. Okay, so what will happen is we can start accepting, all right, those proton ions, all right, or we can start donating those proton ions or those hydrogen ions to help neutralize, all right, whatever it is that's causing that pH to shift in one direction or the other. So in our bodies, you have carbonic acid, which is a weak acid, or we can have a weak base, which is bicarbonate, and both of these help to buffer the blood. All right, so they keep that blood in that 7.35 to 7.45 range. All right, and the exciting thing is you get to learn about in 211 what happens when those buffers start to have issues and your pH gets out of that normal range. But that's in 211. Okay, so what is the general relationship of a hydrogen ion and the pH value? This is that inverse relationship that I was telling you about, okay? So the greater the hydrogen ion concentration, the lower your pH will be, okay? And vice versa, okay? So remember, it's an inverse relationship, hydrogen ion concentration and the pH value. As one goes up, the other must come down, and vice versa. And when we do change, like I was saying before, when we shift from one number like 6 to 5, 2 to 1, right, it will be a 10-fold difference, an increase or a decrease, depending on which direction you're moving in. Okay, but just know it's a 10-fold difference. All right, so let's jump into the next subject here. All right, we're going to start talking about macromolecules. Right, again, going in that organizational system that we're talking about, starting off really small, and we're slowly getting to the bigger biological structures here. We started with atoms and molecules. Now we're going to work up to macromolecules. All right, so we're going to talk about the biological macromolecules. So, all right, macro meaning big. These are just going to be the large organic molecules that our body makes, right, or that we consume through our diet, for example. Okay, so these macromolecules are always going to contain carbon, right? They're going to be biological or organic. They have to have carbon in it, hydrogen, and oxygen. Okay, now some of these macromolecules will also contain nitrogen, phosphorus, or sulfur. Okay, we'll talk about that. All right, so these carbon skeletons that we have, all right, you're going to hear the term hydrocarbon, and if you dissect the word hydrogen and carbon, all right, so these hydrocarbons will only have carbon and hydrogen. Okay, so you got to become familiar with this other term here, what we call functional groups. All right, these functional groups, all right, are these groups that are attached onto these molecules. All right, a lot of them will be polar. All right, but what will happen is, all right, some of these functional groups can also act like acids. Right, if they act like an acid, then all right, we give them the nomenclature of a carboxyl group. And some of those functional groups will act as bases, all right? And usually that's because they contain, all right, a nitrogen in that group, and we call those amine groups. Okay, we'll discuss that here in a little bit. All right, so let's start off by talking about some of these um, macromolecules. We're going to start off with lipids. Okay, and when you hear the term lipid, or when you're reading lipids, I want you to think of fats. Okay, but one of the important properties of lipids is that they are water insoluble. Okay, so what does that mean? If you've ever cooked boiled water, made pasta, sometimes when you're making pasta, they encourage you to put a olive, whatever type of cooking oil that you may be using. Okay, and if you've noticed, it will kind of not congeal, but it won't separate. It won't dissolve into the boiling water. It'll kind of float there. It doesn't mix, and that's what happens. Okay, so when we talk about water insoluble, what it basically means is that whatever this is that we're talking about will not dissolve into the water. All right, so lipids do not dissolve into water. Okay, so you need to know this. We're going to go through this quite a bit when we're talking about throughout this class and in the next class in 211, some of the functions of lipids. Right, one is that they are stored forms of energy. Okay, your body loves fats. It's an awesome source of energy. Okay, you'll get to really appreciate the energy sources or the fat as an energy source later on in the course. All right, but right now it is a stored form of energy. Okay, the cellular membrane, the plasma membrane, is going to use lots of these lipids, all right, in its construction of the plasma membrane. And then in chapter 17, you'll get to learn about the hormones. All right, but lipids are used in the synthesis of hormones, and the hormones are that chemical messenger that help with certain biological functions in your body. Okay, so there's four classes of lipids. Okay, triglycerides. All right, and the triglycerides are going to be one of the most diverse, excuse me, not diverse, but abundant forms, all right, of lipids in the body. All right, then you get the phospholipids, all right, which are the most common form of lipids that you'll see in the body. Steroids, and then eicosanoids, which are the locally acting form of hormones. And we'll briefly talk about all of these. All right, so let's jump into the first one here, the triglycerides. Okay, triglycerides, again, this goes back to the functions of lipids, and that's energy storage. These are long-term energy storage. Okay, so when you eat something or your body breaks it down, it's going to start to build triglyceride molecules, and if you don't use them immediately for energy, well, then your body wants to store them for a rainy day. Okay, and so it will store these triglycerides, all right, in the adipose cells. All right, and so to understand triglycerides, you need to know the molecule is made up of, all right, a glycerol, all right, group, and 3 fatty acid chains. Okay, and the fatty acid chains can vary. They can be long, they can be short, all right. They can have double covalent bonds or single covalent bonds, all right. But keep in mind, all right, that they don't have to all be the same type of fatty acid that's attached to the glycerol group, all right. So when we refer to saturated fats, that means that these types of triglycerides, all right, they do not have any double bonds. Okay, and then when we talk about unsaturated, all right, these triglyceride groups will have 1 double bond. Now, if we talk about polyunsaturated, obviously poly is many, they'll have 2 or more double bonds. Okay, so saturated, no double bonds, unsaturated, 1 double bond, and the polyunsaturated are going to have 2 or more. Okay. All right, so big concept to know with triglycerides, they store energy. Okay, they do not release energy. Oh, excuse me, do not release. I don't know why I said that. All right, but they will eventually release energy when your body needs it. Okay, so they are one of the more common forms here. All right, they'll be used for long term. But also you'll see the functions of triglycerides and lipids is that we'll see them for structural supportive items, right, cushioning and insulation, okay? So when we store the triglyceride molecule, we're going to store it in a specific type of tissue. That's going to be our fat tissue or the adipose tissue, right? And so when we want to store these triglycerides, when we don't, energy requirements are low, but we have a lot of triglycerides floating around in our body, right? We're going to undergo this process of lipogenesis. Now, lipogenesis, lipo is fat, genesis is to create. So we're going to create fat tissue, okay, in our body, okay? Now, when we are in need of energy, all right, and we start to break down our fats, right, that process is known as lipo, again, lipo or lipo, is going to be the fat portion, and then lysis means to break down. So we are going to start to break down those triglyceride groups that are stored in our adipose tissue there, okay? All right, and this picture here is basically showing you, here's your triglyceride group, okay? That's those three red balls here. That's going to be our glycerol molecule. And then these black balls with the blue balls attached to it, those are going to be the individual fatty acid chains. And you can see here, all right, these fatty acid chains are not all the same. They vary in length and they vary in arrangement, okay? But they're all attached to the glycerol group. So when we start to break down, all right, these triglycerides, what we'll do is we'll detach the fatty acid chains from the glycerol group, and then we'll just start chopping up these fatty acid chains to make energy. All right, the next type of lipid is the phospholipids, okay? These phospholipids are in huge abundance in our body, and the reason why is because they make up, all right, a significant amount of our plasma or cell membranes, okay? And a phospholipid is going to be a molecule that exhibits both polar attributes, all right, and non-polar attributes. So we refer to those types of molecules as amphipathic, okay? So they have both polar and non-polar components to them, okay? They are similar to the triglyceride group, except instead of having the three, all right, fatty acids that hang off of the glycerol group, these guys, okay, have two, okay? And so in this situation, all right, we've got that circular structure that is called the hydrophilic head, all right, that's the water-loving head, okay? And then we have the tails, all right, what we refer to as the hydrophobic tails, okay? They are nonpolar, they will not dissolve in water, so they are water-fearing. And the head, all right, is that glycerol makeup, all right, also has a phosphate group to it, but it is polar, okay? And so therefore it's water-loving, okay? Okay. The next type of lipid is going to be the steroid component. And again, these are specifically hydrocarbons, which means that they are hydrogen and carbon molecules. And they are going to have a ring component or structure to them, all right, multi-ringed, and it varies, all right. You'll have some that have 4 rings, some that will have 3 rings, and then some that will have 1 ring. But these rings will have variations of the number of carbons inside of them. 6 carbon ring, 5 carbon ring. All right, that just varies. That's not really too important, but just to understand that those carbon rings and the number of rings will vary, okay? And then you'll have these side chain or these groups that are attached onto the rings that come off, all right? So an important type of steroid is going to be the cholesterol component. That's huge because it makes up an important part of our animal. We fall under the animal component or classification, but it makes up a huge component of our plasma membranes. Right? It's important. Cholesterol actually will provide a certain amount of stability to our plasma membrane. So that's why it's good to actually have cholesterol in your body. All right. So when you get your blood checked, and they'll monitor the amount of cholesterol. All right. It's not necessarily a bad thing to have cholesterol floating around in your blood, but you just want to make sure that you're using that cholesterol and that it's not going to be kind of clogging up your blood vessels there. But also, cholesterol is important because that's how we make steroids. Right? It's what we call a precursor, which is one of the items that we need in the beginning process of making our steroids. All right? It's an ingredient. Okay, so for us to make our steroids, we need to have cholesterol present. All right? And then also bile salts, which are important too, because it's the bile salts that help us to break down, all right, certain substances in our diet, all right, mainly fats. Okay, your liver makes the bile, all right, but in order to make the bile, it needs the ingredients for that. Okay. All right, and then finally, the last classification of lipids, not classification, but one of the subdivisions or categories of lipids is the eicosanoids. All right, the eicosanoids, again, are locally acting hormones. All right, they actually come from, all right, arachidonic acid. And this is important because in your plasma membranes, all right, remember we were talking about the phospholipids? Well, if you damage that plasma membrane, you have an enzyme, and an enzyme is a protein that helps with chemical reactions. Okay, they can start off chemical reactions. And what will happen is when you get damage to these plasma membranes, those phospholipids, all right, well, there's an enzyme called phospholipase A2, and that enzyme breaks down these phospholipids into arachidonic acid, and that arachidonic acid will undergo a series of chemical reactions. And those chemical reactions, we call those an enzymatic cascade, which is a series of these chemical reactions that produce, all right, these guys down here, all right, these eicosanoids. And these eicosanoids have a lot of different functions, but one of the common functions that we see from these four eicosanoids is inflammation. Inflammation is usually associated with tissue damage or cellular damage. Okay, we'll also see them when in certain situations for our nervous system, but we'll talk more about that later on. But you see these different classes for these eicosanoids: prostacyclins, prostaglandins, leukotrienes, and thromboxanes. They play several different roles throughout the body. One of the main ones is going to be inflammation, swelling. So when you damage yourself, that's why sometimes when people have hurt themselves, you'll hear somebody say, well, why don't you take an anti-inflammatory for that? And what that anti-inflammatory will do will help to decrease inflammation or that swelling. And how it does this is that it blocks one of the enzymes, all right? And if you block the enzyme, then you're pretty much throwing a monkey wrench into that chemical cascade, that enzymatic cascade, and we can't form. Basically what we're doing is we're trying to prevent the formation of any of these four classes of eicosanoids. If we prevent their formation, then we can prevent or decrease inflammation, amongst other things, pain. There's several different things that these four classes of eicosanoids are involved in. Okay? All right, so when you look here, we talk about the clinical view, all right, the importance of these fats, a couple things that you want to understand. All right, when we talk about fats, all right, if something is a solid at room temperature, all right, we usually refer to it as a fat. If something's a liquid at room temperature, we usually refer to that as an oil. Okay, but they're essentially the same thing. One's in liquid form, one's in fat form. So most animal fats, right, when we're talking about saturated fats, those will be solid at room temperature. Okay, so we really don't want to have animal fats, okay, because at room temperature, if they're a solid, that's not necessarily a good thing, especially if anything that has the potential to be solid is inside of your circulatory system. That will be bad. Okay, although your circulatory system shouldn't be at room temperature because room temperature is 70 degrees and your body temperature is much higher than that. All right, so when we talk about vegetable fats, okay, we refer to those as unsaturated, and most of those will be liquid at room temperature, and that's why we usually consider those to be the healthier alternative. Okay, and then the bad guy here that we don't like to see is this guy, trans fats. All right, we can all agree that trans fats are bad news. All right, because we talk about partial hydrogenation, and that's the process that creates these trans fats. All right, and it's not a good thing. All right, in a lot of cases, some people consider it to be not so much a natural phenomenon because of this chemical process that they have to go through. All right, but these trans fats have proven to increase your risk of a heart attack or stroke. All right, so we can all agree you can avoid trans fats, and in fact, in New York City, they actually outlawed trans fats. All right, so for your health benefit and mine, it's a good thing. All right, a couple other types of lipids, all right, are glycolipids. Okay, and if you look at glyco, all right, basically a glyco is a sugar group. All right, so it's a lipid is a fat molecule with a carbohydrate group attached to it, which is important. All right, you'll see these types of molecules sitting or floating in the plasma membrane, and it's going to be very, very important because it's we see that when something is going to bind to a cell, okay, and that's important for certain types of certain types of synthesizing processes that go on, especially if that cell is a cell that makes maybe like a hormone, like a beta cell. Right? It's important to get those cells activated and making stuff if that's their function and the role, and these glycolipids help in doing so. All right, and then you've heard of fat-soluble vitamins, A, E, and K. There's one missing on there. All right, vitamin D. Okay, we're starting to see that vitamin D is no longer really considered to be a vitamin, although in some of the literature you're still seeing it placed there. So don't rule that out. But again, fat-soluble vitamins are going to be these vitamins or these what we call coenzymes that will be able to dissolve into fat. Okay, and that's why you can reach toxic levels because they can actually be stored in fat. So which class of lipids form the cell membranes? This is a great test question here. All right, phospholipids fall into that category. Okay. All right, moving into the next type of macromolecule are carbohydrates. Okay, sugars. Okay, but what we're going to see with carbohydrates is, all right, you're going to have, all right, carbon molecules that are going to have either a hydrogen molecule attached to it or an OH molecule attached to it. Okay, so the three elements or atoms that are found in carbohydrates are going to be carbon, hydrogen, and oxygen. So the chemical formula that we're going to use for these carbohydrates is noted above. You don't have to memorize it, but it's good to be familiar with it. All right, CH2O, all right, are going to be inside the parentheses. Then outside you see N there, and the N is just the number of carbons that are going to be found in this molecule. Okay, so for example, glucose has 6 carbons. So it'll be C6H12O6. Okay. So when we're talking about carbohydrates, our monosaccharides are what we consider to be the simple sugars. All right. And you'll see this term here called monomers. And a monomer is basically, I'll show you a picture here of a monomer real fast. All right, is going to be one simple sugar molecule all by itself. Okay. But what will happen is, and in the body, all right, when we want to store that simple sugar, that glucose molecule, All right, well, what your body will do is it will start to make a chain, all right, of these simple sugars, of these glucose molecules, and it'll start to string them along, all right, into this configuration here, okay? And when that occurs, we start to form, all right, our, um, our polysaccharides, okay, which is glycogen. Okay, so basically you start to string along, because once you get two simple sugars or monomers put together, then you have what's known as a disaccharide. So going back to this slide here, our monosaccharides are going to be our simple sugars, okay? And then when we take two monosaccharides or two simple sugar molecules and we attach them to one another, then we get a disaccharide, di meaning two, which is two monosaccharides. And then when we start to string along, all right, a whole bunch of our monosaccharides, all right, then we get what is known as a polysaccharide, okay, which is many monosaccharides. So jumping here onto this slide here, you really want to know that glucose is going to be the most common monosaccharide. Your body loves glucose, and in fact, your brain craves it. Okay, your brain is numero uno. That's it. Numero uno, number one. That is going to be, all right, the number one organ for glucose. It gets top billing. It gets priority. Okay, so glucose is pretty much the primary nutrient or energy source for your cells. So that's why its concentration in your body, in the tissues, in the blood sugar, for example, is so critical, okay? Because we want to keep providing our cells with the required energy that they need to sustain whatever their biological functions are, okay? So we talked about glycogen. That is our polysaccharide, all right? And you want to know the two locations in which glycogen is going to be stored. So when we have too much glucose floating around in our body, again, your body likes to store things away for a rainy day. So what happens is your liver, primarily your liver, but also your skeletal muscle cells, all right, they are going to store that excess glucose, all right, as glycogen, okay? So great test question. I keep asking it every semester. What two organs, all right, or tissue are going to store glycogen? That's going to be the liver and skeletal muscle, okay? And that process of making glycogen, you need to know this, is called glycogenesis, okay? Glyco being glycogen and genesis is to make or create. So glycogenesis is the creation of glycogen in the liver and skeletal muscle. Okay? Now, when your energy levels are low, so your blood glucose levels have dropped, or your blood sugar levels have dropped. So now we've got to take that stored glycogen in the liver and stick it into the blood. So to do that, all right, we're going to start breaking down that glycogen. All right, the chemical process that we utilize is hydrolysis. So the liver is going to hydrolyze the glycogen. It's going to break it down into individual glucose molecules. And that process is called glycogenolysis. So the first part of that word is glycogen, and lysis is to break down. So glycogenolysis is the breaking down of glycogen into glucose molecules, okay? And the liver is also a wonderful organ because it can also, all right, make glucose from sources that are not carbohydrates, fatty acids, for example, proteins, lactic acid, all right? These are non-carbohydrate sources. So the liver undergoes the process of what we call gluconeogenesis. It makes new glucose from non-carbohydrate sources. If you look at the term here, gluco, all right, is going to be glucose. Neo meaning new. All right, so we're going to make new glucose from non-carbohydrate sources. That's gluconeogenesis. We've already seen this picture here. Okay, so when it's time to make our glycogen, we take our glucose molecules, we string them along and make this molecule, that's glycogen. And then when it's time for energy, okay, we start to snap off these individual monomers of glucose. So we snap off that one, we snap off that one, snap that off, we undergo glycogenolysis. We wind up with glucose molecules floating around. Okay? All right. A couple other types of carbohydrates. So the hexose monosaccharides, these are the isomers. Remember we learned about isomers. These are structures that have the same molecular formula, but their structural formulas will be different. Galactose and fructose are some of those examples. We have our pentose sugars. We'll talk a little bit about those when we get into RNA and DNA. All right, ribose and deoxyribose. Then our disaccharides, these are going to be when we take those two simple sugars, we stick them together to make a disaccharide like sucrose, our common table sugar, and lactose, all right, milk sugar, we're familiar with those, okay. And then obviously our polysaccharides, an example was the glycogen that we saw that we make. Starch is another example that we see like in potatoes, all right, huge for us. Cellulose, we see that in plants, but unfortunately we can't digest it very well, and so it makes an excellent source of fiber, all right, which is a non-digestible structure, and it just kind of helps to kind of clean us out. So this slide here is basically showing you some pictures here of our monosaccharides, all right, our hexose sugars, galactose and fructose, all right, and then you can see our 5 carbon sugars here. All right, and then we can see our disaccharides, table sugar, our sucrose, lactose. All right, this is milk sugar, or maltose there from malt. So what is the repeating monomer of glycogen? That will be glucose. And where is glycogen stored in the body? All right, it's mainly stored in the liver and skeletal muscles. All right, moving on to the next macromolecule, and that's going to be our proteins. Now this is probably one of the most important slides. So if you're watching this and you're taking notes, you should put a star next to this, because this is showing you all the different functions for proteins, okay? And so as you can see, we'll talk about several of these this semester, all right? But to name a few, all right, our proteins act as enzymes or catalysts. What that means is they help to start chemical reactions and get things going, or what we refer to in our body as metabolic reactions, all right, that help to serve a biological function, like making something or breaking something down. But these types of proteins help to get the party started, okay? They also help with defense, and what that means is when we're talking about antibodies, for example, and we've been hearing a lot about antibodies, especially with the coronavirus, all right? So these proteins act in the formation of antibodies, all right? And there's several different classifications for antibodies, all right? They also help with transport. How do we get things in and out of cells, or how do we move things within the cells, all right? They help with transport, okay? Also with structural support. So when we synthesize or make proteins, they play a big role in what we call the cytoskeleton, for example, which is the cells, the individual cells actually have a skeleton inside, not made of bones or whatnot, but they're actually made of proteins that help to offer support. All right, movement, regulation, and storage. We'll get into all these as we move along, but you just want to familiarize yourself with those different functions there, okay? So proteins, all right, they're not just created and instantly become a protein. We have to build them up, all right? And so there's building blocks to proteins, and the names of those building blocks are called amino acids. And so what happens is your body starts to kind of string these amino acids along, and as it strings them along, it'll eventually create a protein. We'll talk about that in a second. So we have 20 different types of amino acids that are found in living organisms. And on these amino acids, they have to have two functional groups. The first one is amine. Remember we talked about that? That's almost like the basic portion of the amino acid, but it contains a nitrogen group in there, and then we'll have our carboxyl group, and that's close to like the acidic portion. Okay, but both of these, all right, functional groups, all right, are going to be attached to our amino acid here. Okay, and also in the amino acids we'll have hydrogens and oxygens. All right, and in some of these situations, all right, we'll have what's known as an R group, and these special R groups help us to distinguish one type of amino acid from another type of amino acid. Okay, so when we start to attach these amino acids to one another, we do so through what we call a peptide bond. And it's important that you know that. All right, and when we create these peptide bonds, all right, we undergo what's known as a dehydration synthesis reaction. And basically what that reaction is, there's a byproduct that's given off. All right, so as we make these peptide bonds, as we start to undergo that linkage of amino acids to one another, we get a byproduct of that reaction, and that's water, which is kind of nice. All right, so consider that as you start to learn and go through these processes here. All right, and on one end of our structure, as we start to link these amino acids, all right, we're going to have maybe at the very end or at the very beginning, depending on your point of reference, all right, we're going to have what's known as a free amine group on one end, and then we'll have a free carboxyl group on the other end, or we'll have an N-terminal or a C-terminal end. And let me just show you, because it's always easier to show you in the picture here. All right, so what this picture is showing you, here's our amino acid. All right, so on our amino acid, we have an amine group, all right, and we have a carboxylic acid group here, okay? Then you have some specific, all right, grouping here, what we call the R group, that helps us to differentiate between one amino acid and another, okay? So what happens is we start to link, all right, these amino acids or string them along. They undergo that dehydration synthesis reaction, and our byproduct is water. Really nice. All right, but as you can see, we start to link these amino acids together. But at the very beginning of our structure, you can see we have an amine group, an N-terminal. And at the other end, we have our carboxylic acid, or what we call our C-terminal group. All right, so at one end, you're going to have the N-terminal. At the other end, you're going to have the C-terminal. And we just keep linking amino acids on and on and on and on. Okay, so now we're getting up to, all right, we have these long strands of amino acids. So when do we get the protein? Well, first, before we get to the protein, if we have a string of amino acids and it numbers between the values of 3 and 20, then we have what's called an oligopeptide. Okay, and as we continue to string more amino acids onto that, if we get to the values of 21 to 199 amino acids, then we have what's called a polypeptide. We don't have a protein until we get to a value of 200 and more amino acids. Don't ask me where that number came from or who decided that, okay? All right, but when we get to that value of 200 and more amino acids, then we have protein, okay? Now, some of these proteins will have a carbohydrate group attached. Then we refer to those as glycoproteins. All right, and we'll see that that's very important in our blood typing. All right, so we have our glycoproteins, our ABO blood typing, all right, and which helps our body to identify blood that is ours and blood that shouldn't be there, and that can be a problem. Again, we'll talk about that in 211. All right, so what are the monomers of proteins? The monomers, or the building blocks of proteins, are amino acids. And the bond that links them are peptide bonds. Okay, important to know. All right. So a couple things about our amino acids. We're going to have our polar and non-polar amino acid groups. All right. So it is helpful to understand that, all right, when we're talking about nonpolar and our polar amino acid groups. All right, let's just jump into the last part of the macromolecules, and this is going to be the nucleic acids. All right, nucleic acids you may have heard before, all right, when we're referring to DNA or RNA. And basically what that is our genetic material. Basically the DNA is our blueprint, our genes, our genetic blueprints, all right, of what makes us us. And that is going to be found, all right, on our DNA and in our RNA. Okay, so there's two types of our nucleic acid, the deoxyribonucleic acid, which is going to be our double-stranded nucleic acid. And this is where you'll find the DNA is going to be found in these structures called chromosomes inside the nucleus. And believe it or not, you actually have some chromosomes in your mitochondria. Mitochondria are the powerhouse of the cell. They make a lot of the ATP, which is the cellular energy currency. Okay, but you do have chromosomes in our mitochondria, and those chromosomes come from mommy. Okay, none from daddy, only from mommy. The other type of nucleic acid is going to be RNA. Okay, these are single-stranded nucleic acid, and they'll also be found in the nucleus, but also within the cytoplasm. That's the goo, the gel inside the cell. Okay. So keep in mind, and again, I'm not going to get into a lot of the details for this, all right? But keep in mind when we're talking about these nucleic acids, all right, we do have some basic building blocks for these nucleic acids. And these basic building blocks are called nucleotides, okay? And when we're dealing with this, and again, I'm not going to go into this right now, only because I want to get to this last concept of nucleic acids, because we're going to have, we're not in this course, we're not going to delve really too much into the basics of cellular DNA. All right, that's going to be more of a genetics course or a biochemistry course. Okay, but what I want to get into is this last structure here. All right, of nucleic acids, what we call adenosine triphosphate, ATP. And ATP is a very important molecule because this is how we transfer energy within the cells. Okay, and so basically this slide is telling you, all right, that nucleic acid is made up of a couple different components. One, what we refer to as a nitrogenous base, which is, in this case, adenine is our nitrogenous base, which is attached to a ribose sugar, right, which is going to be a 4-carbon sugar. Okay, but most importantly is this concept here. You have 3 phosphate groups attached to, all right, your adenosine, all right, which is that 5-carbon sugar there and that nitrogenous base. Okay, and these phosphate groups are covalently bonded to one another, and when we break these bonds, that's how we release the energy, and that's how we are able to undergo certain processes inside the body. All right, these other 2 nucleic acids, NAD and FAD, nicotinamide, adenine dinucleotide, and FAD, these help with the formation or the creation of that ATP. Okay, so here's that molecule I was telling you about. Okay, so we see adenosine here all the way over on the right, which is made up of a nitrogenous base, the adenine, and then our 5-carbon ribose sugar. Right, but the really important thing that I want you to see here is this triphosphate group. Okay, so you have 3 phosphate molecules that are bonded to one another. Okay, and these bonds here and here have a ton of energy. So when your cell needs energy somehow, what it will do is it'll snap this bond right there. And when that happens, this phosphate group and all the molecules attached to it will just pop off. Okay, so you'll have a free-floating inorganic phosphate. I don't know why it's doing that. All right, that should be a P. So you have this inorganic phosphate floating around. But that process of snapping off that phosphate group will release energy. And so the cell can do stuff then when that energy is released. And we'll talk more about the importance of ATP and whatnot, but I just kind of wanted you to kind of have an idea of what that looks like. Okay, I'm going to stop the video here and let you kind of soak all that information in, and then we'll talk about tissues here in a moment.